Hey, this is Kyle again, and I'm here to talk about part A3 of exam 3. So, let me describe the situation we have. It's a adiabatic saturation temperature experiment. So, we have what is essentially an infinitely long tube, and we have a stream of air going through the tube, as well as a stream of water going through the pipe. So this stream of air has a few variables we want to keep track of: the mass flow rate, the partial pressure of water going in, the temperature going in, the mass flow going out, the temperature going out, and the partial pressure of water going out. This stream of water, all we really need to know is that it's kept at a constant temperature. We'll call it TW. So as I said, this pipe is infinitely long. So since it's infinitely long, we know that the air flowing out of the pipe is going to be saturated fully. And since it's fully saturated, we know that this saturation, or this pressure, partial pressure of water going out is essentially equal to the pressure of water at that temperature, the saturation pressure of water at that temperature, or at the temperature of that water. So now we want to do an energy balance for this situation. So it's a steady state situation, so we know that the enthalpy in is going to equal the enthalpy out. So I'll make an equation for the enthalpy in as well as the enthalpy out. We want to start off with the mass flow rate. We're going to multiply that by the heat of vaporization of water. So now we essentially want to have the amount of water flowing into, or evaporating into the airstream. So that's what we're going to need to do is this next part. So it's important to keep track of your units in an equation like this. So our mass flow rate is kilograms per second. This is often given in kilojoules per kilogram. So now we want kilograms of water. So we can get moles of water going in with our partial pressure of water in the air initially over RT. And as I said, that's gonna be moles of water per cubic meter. So to get it to kilograms, we want to multiply by the molecular weight of water. So that'll be, so originally we had what? Moles water over meters cubed of the system. Then we multiplied by the molecular weight, so kilograms per mole. And that's of water, so that means this moles will cancel, this moles will cancel. And we have kilograms of water. That's what we want on top, but we do have this cubic meter on the bottom, and we still have this kilogram out here, kilogram of air. So we need to get rid of that. So to do that, we can kind of just invert this. So we have RT on top, and we're going to do total pressure times the molecular weight average of the air-water system. So that's going to get our cubic meters of the system on top and our kilograms of the system. So that's system I'm just using for the air-water mixture. So this is essentially going to be the same thing as this because the kilograms of system and the kilograms of air, because it's majority air, so we can think of those as canceling. These cubic meters will cancel. And we're left with what we wanted, the kilograms of water on top, which is what this heat of vaporization is given in. So that's good. Now we need to include the sensible heat. So that can be done by the heat capacity times a temperature difference. Normally we would do the temperature in minus a reference temperature, except in this case, we actually do not have a, or we're going to set our reference temperature equal to 0 to keep it simple. So we can just say it's Cp times T1. So now we have our enthalpy in equation, we're going to make an out equation, which is going to be pretty much the same equation. We're just going to switch it with the variables for the air flowing out. So it'll be m air, heat of vaporization, and as I said, the partial pressure going out is the saturation pressure at that temperature of water times the molecular weight of water over RT times RT over total pressure times the average molecular weight. And again, we want to include the sensible heat, so we can do the heat capacity times T2, because once again, our reference temperature will be 0. So now that we have our enthalpy in and enthalpy out, we can set those equal. So first we can see some obvious cancelizations. So we can cancel those out, cancel that out. And now when we set them equal, we can draw out some of the similar terms. We'll do that over here. So So that's our enthalpy in, and we can set that equal to, and I think I'm running out of room, so I'll just put it below, the enthalpy out. Alright, so now we can reorganize that to kind of combine some common terms. And first we can obviously see that m air is going to cancel, the mass flow rate of air is going to cancel. I need some more room, so I think I'm going to erase these enthalpy equations since I just rewrote them. So as I said, I can do some combination here. So let's see. So I think I can pull out. Let's see. So we're just going to combine everything to one side to do the algebra real quick. So lambda. W over P, so average plus CP plus T1, and then we can subtract lambda PW saturation over T2. Alright, so then we can see that this term and this term have some commonalities. 0. So we can draw out molecular weight of water, the average molecular weight, and the total pressure, and the lambda, heat of vaporization. So heat of vaporization times molecular weight of water over total pressure times average molecular weight. and we need the terms that aren't common to be included still. So that's this partial pressure at the entrance point. So that would be PW1, and subtract the partial pressure at the outlet, which is, as we said, the saturation partial pressure. And then we can do the other terms. So that has CP in common. And then it has T1 minus T2. And we're going to move that back to the other side. This, when I subtracted this onto this side, I should have had parentheses there. So I just drew out the CP on this side. On this left side, I drew out a heat of vaporization times the molecular weight of water over the total pressure times the average molecular weight. And I wrote down up in the top right the equation we got in A2 for the wet bulb. And it looks very similar to this equation we got in the adiabatic saturation temperature experiment. So the only difference really is we have these differences are basically flipped. So T1 minus T2 in the adiabatic saturation temperature is the so the initial temperature minus the second temperature, where here we have the air temperature times the surface, or minus the surface temperature, and then the pressures are flipped. So, or the partial pressures, this is the partial pressure of water at the surface, which is higher than the partial pressure of water in the atmosphere. And this one is the initial partial pressure of water minus the saturated partial pressure at the outlet. And in that case, this is going to be lower than that. And then, as we can see, when we did A2, we didn't include molecular weight, but that depends on the unit of the heat of vaporization. So in this section, we assumed that we needed to add the molecular weight, so I went ahead and showed where it would be added. So if we multiply the total pressure and the average molecular weight onto this side, we get the same equation on the right side that we had, and then we have the same equation on the left side that we had. All that's changed is both parentheses are flipped. Well, all that does is flip the sign, and since both are flipped, it's essentially the same equation for both scenarios. And what that is kind of showing is that the basically the temperature at the outlet in our adiabatic saturation temperature experiment is going to be the same as the temperature that's read for the wet bulb for the wet bulb temperature.